In the name of God. Fluid Mechanics from Frank M. White, 7th edition, Chapter 1. The new update of Microsoft Whiteboard is an ability to study in a blackboard type. So our two previous courses, static and dynamics, were studied in whiteboard, and fluid mechanics will be studied in blackboard type. So anyway, we are going to have an introduction to fluid mechanics. Introduction. First, we have a preliminary remarks where there is a definition of fluid mechanics. Is the study of fluids either in motion or at rest. Both gases and liquid are classified as fluids. So gases and fluids considered as gases and liquids. Let me have a fraction here. Gases and liquids. And the number of fluid engineering application is enormous. Breathing, flow, swimming, pumps, fans, turbines, airplane, ships, rivers, windmills, pipes, missiles, icebergs, engines, filters, jets, and sprinklers, and other applications. When you think about it, almost everything on this planet either is a fluid or move within or near a fluid. So the fluid mechanics is an important science in the interpreting the phenomenon in the earth, and also where there is a fluid also available, for example, maybe on other places without gravity or non-gravitational force. The essence of subject of fluid flow is a judicious compromise between theory and experiment. Since fluid flow is a branch of mechanics, it satisfies a set of well-documented basic laws, and thus a great deal of theoretical treatment is available. However, the theory is often frustrating because it applies mainly to idealized situations, which may be invalid in practical problems. The two chief obstacles to a workable theory are geometry and viscosity. The basic, so we have many assumptions and simplification during the, for example, assumption against viscosity and geometry. Main assumption. The basic equation of fluids will be described later. are too difficult to enable to analyze to attack arbitrary geometry configuration. Thus, the most textbooks concentrated on flat-bladed circular pipe and other easy geometries. It is possible to apply numerical computer techniques to complex geometries, and specialized textbooks are now available to explain the computational fluid dynamics approaches and methods. This course will be present many theoretical results while keeping their limitation in mind. The second obstacle to a workable theory is the action of viscosity, as we write here. Viscosity, which can be neglected only in certain idealized fluids, will be described in the later in this course. First, viscosity increases the difficulty of the basic equation, although the boundary layer approximation found by Prandtl has greatly simplified viscous flow analysis. Second, viscosity has a destabilizing effect on all fluids, giving rise at frustratingly small velocities to a disorderly random phenomenon called turbulence. The theory of turbulence flow is crude and heavily backed up by experiments, yet it can be quite serviceable as an engineering estimate. This textbook only introduced the standard experimental correlation for turbulence time mean flow in next chapters. Meanwhile, there are advanced texts on the both time mean turbulence and turbulence model, and on the newer computer-intensive direct numerical simulation (DNS) or fluctuating turbulence. With this definition and introduction, there is theory available for fluid flow problems, but in all cases it should be backed up by experiment. Often the experimental data provide the main source of information about specific flows, such as the drag and lift of immersed bodies. Fortunately, fluid mechanics is a highly visual subject with good instrumentation and the use of dimensional analysis and modeling concepts. The experiment provides a natural and easy complement to the theory, and we should keep in mind that theory and experiment should go hand in hand in all studies of fluid mechanics. First of all, and before continuing to the introduction to the fluid mechanics, we have to study how to solving a problem. So we are going to describe problem solving techniques. Fluid flow analysis is packed with problems to be solved. The present study has a lot of problems and solutions. Solving a large number of these problems is a key learning to subjects. One must deal with the equations, data, tables, assumptions, unit systems, and solution chains. The degree of difficulty will vary. We will work on to sample the whole spectrum of assignments with or without the answers in the appendix of the book. Here are the recommended steps for problem solutions. 1. Recommended One, read the problem and restate it with your summary and the result desired. and restate it with your summary. On the results desired and the desired results. 2. From tables or chart, gather the needed properties, data, density, viscosity. So we have to use standard tables from tables available. Gather the needed property data such as density, viscosity, and Make sure you understand what is asked. A student are apt to answer the wrong question. For example, pressure instead of pressure gradients, lift force instead of drag force, or mass flow instead of volume flow. Read the problem carefully. So make sure you understand what is asked. Make sure you understand what is asked. For example, pressure, for example, that equals to pressure gradient and 4. Make a detailed labeled sketch of the system or control volume needed. Make a detailed labeled sketch of the system or control volume. Five. Think carefully and list your assumption. You must decide if the flow is steady or unsteady, compressible or incompressible, viscous or inviscid, and whether a control volume or partial differential equation are needed. 6. Find an algebraic solution if possible. Excuse me. Find an algebraic solution if possible. Then if a numerical value is needed, use either the SI or British unit system to be described in the next section in this chapter 7. Report your solution, label it with the proper units and proper number of significant figures that the data uncertainty allows. Report your solution. If possible. Then if a numerical value is needed, use either the appropriate system of units. Let me make a correction here. The concept of fluid. The next description in this chapter is the concept of fluid. From the point of view of the fluid mechanics, all matter consists of only two states, fluid and solid. The difference between the two is perfectly obvious to the lay person, and it is an interesting exercise to ask a lay person to put this difference into words. The technical distinction lies with the reaction of the two to an applied shear or tangential stress. So we have two different matter, solids and fluids. Newtonian fluids or non-Newtonian fluids. The technical difference is the type of reaction. Against external forces or shear stress. Tangential stress. A fluid can state here. Can say a solid can resist a shear stress by a static deflection. A fluid cannot. Solid can resist a shear stress by deflection. A fluid cannot. Any shear stress applied to a fluid, no matter how small, will result in motion of that fluid. The fluid moves and deforms continuously as long as the shear stress is applied. As a corollary, we can say that a fluid at rest must be in the state of zero shear stress, a state often called the hydrostatic stress condition in structural analysis. In this condition, various analysis is available for the analysis of the fluid. So we can write the state of zero shear stress. This is the hydrostatic fluid. hydrostatic fluids. As we know, there are two classes of fluids, liquid and gases. Again, the distinction is a technical one concerning the effect of coercive forces. A liquid being composed of relatively close packed molecules with strong coercive forces tends to retain its volume and will form a free surface in a gravitational field if unconfined from above. Free surface flows are dominated by gravitational effects and are studied in the next chapter. Since gas molecules are widely spaced with negligible coercive forces, a gas is free to expand until it encounters confining walls. A gas has no definite volume, and when left to itself without confinement, a gas forms an atmosphere that is essentially hydrostatic. The hydrostatic behavior of liquids and gases is taken up in the next chapter. Gases cannot form a free surface, and thus gas flows are rarely concerned with the gravitational effects other than buoyancy. This definition is in the introduction to fluid mechanics, and as an example to liquid, gas, and solid states, we can have this picture for more description. This picture shows solids, liquids, and gas. As we have a definition for solids, solids are the matter that resists the shear stress by the deflation, and liquids are the fluids that have a free surface to the air, and in this condition we have hydrostatic. And gas fluids, there is no distinguishable surface between the gas and other gases, and also there is a surface between gas and liquids in two phases of flow. This figure illustrates a solid, resting, rigid plane and other example of the matter classes classified. The fluid in continuum is our next description. Fluid in the continuum form. In case fluid in terms of fluid as a continuum form. We have already used technical terms such as fluid pressure and density without a rigorous discussion of their definition. As far as we know, fluids are aggregation of molecules widely spaced for a gas, closely spaced for a liquid. The distance between molecules is very large compared with the molecule diameters. The molecules are not fixed in a lattice, but move about freely relative to each other. Thus, fluid density or mass per unit volume has no precise meaning because the number of molecules occupying in a given volume continuously change. This effect becomes unimportant if the unit volume is large compared with say, the cube of the molecular spacing. When the number of molecules within the volume with will remain nearly constant in spite of the enormous interchange of particles across the boundaries. If, however, the chosen unit's volume is too large, there could be a noticeable variation in the bulk aggregation of the particles. This situation is illustrated in the figure. This figure shows the density as calculated from molecular mass delta M within a given volume. Delta V is plotted versus the size of unit volume. This figure. There is a limitation volume delta V below which molecular variation may be important and above which aggregate variation may be important. The density rho of a fluid is best defined as this relation. The limiting volume is different and have a standard type of about for all liquids and for gases at atmospheric pressure. For example, 10 minus 9 power mm3 of A at standard condition contains approximately contain 3 multiplied 10 power 7 molecules, which is insufficient to define a nearly constant density relation. Most engineering problems are concerned with a physical dimension much larger than this limiting volume, so that density is essentially a point function and fluid property can be thought of as varying continually in space as sketched here. Such a fluid is called continuum, which simply means that its variation in properties is so smooth that differential calculus can be used to analyze the substance. So we have the definition of continuum for fluid mechanics. It said that its variation is in properties is so smooth in properties is so smooth that differential calculus can be used to analyze the substance. That differential analysis can be used to calculate the substance. We shall assume that continuum calculus is valid for all the analyses in the fluid mechanics science. Again, there are borderline cases for gases at such low pressure that molecular spacing and mean free path are compatible too. or larger than the physical size of the system. They require that the continuum approximation be dropped in favor of a molecular theory of rarefied gas flows. So if molecular distance is comparable or larger than the physical size of the system or control volume. Continuum and it is molecular theory. So continuum is its variation in properties is so smooth that differential analysis can be used to calculate